Hello students, let us start the lecture 3 of the chapter linear equations. In this section it is discussed about the invertible matrices. I am not going in detail what is invertible matrix and what are the elementary properties of the invertible matrices. All you know. What we discuss here is that theorem 11, an elementary matrix capital A, an elementary matrix capital A is always invertible. Recall what is elementary matrix. If I is an n cross n identity matrix, and if we apply a single elementary row operation, then the obtained matrix is called elementary matrix. Okay, then we have here we combine theorem 12 and 13. Mainly in theorem 12 it is given that if A be an n cross n square matrix, then the following are equivalent. The first three statements are given in theorem 12 and the first, fourth and fifth statements are given in theorem 13. I have taken them together. What is the first statement? A is invertible. If we choose A is invertible, then we can prove that A is row equivalent to In. That means after some elementary row operations, A can be taken to an identity matrix. Statement 3, that A is a product of elementary matrices. That means A can be written as E1, E2 dot dot Ek, where each Ei is an elementary matrix. Statement 4 is that the homogeneous system of equation Ax equal to 0 has the only solution x equal to 0. That means it has no non-null solution, non-zero solution or non-trivial solution. And the statement 5 is the system Ax equal to y has a solution for any members to the right hand side. Okay, after theorem 12 there are two corollaries I discuss here. What are these? Let A be an n cross n invertible matrix if a sequence of elementary row operations reduces A to In, then that same sequence of operations when applied to In yields A inverse. What is this? Suppose you are given a matrix capital A and you apply some elementary row operations, and ultimately you are getting the matrix, identity matrix In. Now you take this in and you apply the same set of elementary row operations with the sequence given above, then ultimately we will get the matrix that is the inverse of A. Next corollary is, let A and B are two matrices of order m cross n, then B is row equivalent to A if and only if B equal to PA, where P is an m cross m invertible matrix. Here P is an m cross m invertible matrix. In the last class we discussed the same theorem in some other way. That means if A and B are two m cross n matrices, then B is row equivalent to A if and only if B equal to PA, where P is a product of m cross m elementary matrices. Okay, with this I close this chapter. Okay, we will meet again from the next lecture.